Current, resistance and potential difference. Here we have a circuit to investigate the properties of a resistor. We have the resistor here, with a voltmeter in parallel with it, an ammeter in series, a battery made up of 2 or more cells in series, and a variable resistor, so we can vary the current through and the potential difference across the resistor we're investigating. If we plot a graph of current in amps against potential difference in volts, we get a straight line through the origin. This tells us that current is directly proportional to potential difference. This simply means as you double the potential difference, you double the current, treble the potential difference, you treble the current, and so on. We can write that as Ohm's law, and as I for current, the alpha sign means is directly proportional to V for potential difference. V over I then is a constant, which is the resistance in ohms. So we can say that resistance is the potential difference across a component in volts divided by the current flowing through it in amps. As an equation, R equals V over I, where the potential difference is in volts, the current in amperes, and the resistance in ohms. A metal wire at a constant temperature obeys Ohm's law. Here we have the graph again. If we had a higher value of resistance, it would allow less current to flow at a given potential difference, so it would have a lower gradient. A lower value of resistance would allow more current to flow at a given potential difference, giving a steeper gradient. So the steeper the gradient of a current against potential difference graph, the lower the resistance. Here we have the graph of current against potential difference for a filament lamp, and you'll see at higher potential differences the current is not increasing at the same rate. Therefore the gradient reduces and the resistance must be increasing. If we measure the potential difference and the current at 2 volts, we get resistance as voltage over current, 2 over 2.4, 0.83 ohms. If we find the potential difference and the current at 12 volts, we then find resistance as potential difference over current, which is now 12 over 8.2, giving 1.46 ohms. So you see that the resistance has increased. If we have a graph of current against potential difference for a negative temperature coefficient thermistor, the gradient increases at higher voltages. And if we again find the potential difference in the current at 2 volts, we have 0.5 amps, giving a resistance of 4 ohms. If we look at the current at a potential difference of 12 volts, we get 6 amps. So the resistance now is 12 volts over 6 amps, which is 2 ohms. So the resistance of the negative temperature coefficient thermistor has fallen at higher potential differences. Let's have a little look as to the reasons behind these. Well, in metals like the filament lamp, we have a plentiful supply of free electrons, and they have to pass through the positive ions. They might take a route something like this, travelling from negative to positive, with collision after collision after collision with the positive ions. The electrons collide with the positive ions in the lattice, and that is the cause of resistance. As the temperature rises due to collisions of the electrons with the positive ions, the vibrations will increase. They always were vibrating, but as the temperature rises they vibrate more vigorously. This leads to more collisions between electrons and ions, and so more resistance, which is why the resistance of a filament lamp increases at higher potential differences and higher currents. The temperature has risen. That's what makes the filament lamp glow and give off light. You don't need this particular detail, but briefly, in semiconductor materials such as silicon, we can produce pure silicon, which is a very poor conductor. If we add an impurity, for instance here we have an atom of phosphorus, that adds free electrons, a small number of free electrons. As the temperature of the thermistor rises, the vibration of the positive ions increases in the same way as it does for a filament lamp, which would lead to more collisions, making it harder for any one electron to move through the material. But the rise in temperature gives energy to free more electrons, meaning more charge carriers are available. In a thermistor, this second effect is greater, meaning that the overall resistance of the thermistor falls at higher temperatures.